When Artemis II becomes the first step toward a permanent lunar base, are we building a home or opening a doorway that finally tells us where Earth came from and whether we can outlast it? A single footprint is a headline. An outpost is a sentence written across generations. Artemis is where that sentence begins to hold meaning. Look up and you see a familiar circle, but Artemis treats it like a working frontier, measured, mapped, and slowly made habitable. This documentary follows the program from Artemis II onward, where a crewed Orion tests more than hardware in deep space. It tests judgment under delay, discipline under fatigue, and trust in systems that cannot be rebooted. Because the moon is not just close, it is clean in the way Earth is not. Its surface keeps impact scars, solar particles, and ancient chemistry in place, undisturbed for ages. To read that record, Artemis must become repeatable, and repeatable means architecture. Launch, life support, navigation, power, landing, and return. Every part must work alone, and then work together when schedules slip and margins thin. We begin with Artemis III. You will see why an orbital trial can be the harder truth and why it protects everything that follows. Then the story drops toward the South Pole, Artemis IV, where sunlight skims the horizon and shadows never warm. There, ice hides in permanent darkness, and the rules of survival become chemistry, power budgets, and time. As missions stack, Artemis evolves from a single chain into a redundant network, with more than one lander and more than one way to fail safely. Range expands, science stops being a sprint, and mobility turns exploration into geography. In the process, you will meet the machines that make this possible, from SLS and Orion to competing landing systems built on different philosophies. One path leans on colossal payloads and refueling webs, the other on efficiency and the promise of local propellants. All of it serves one question: can a sustained lunar presence become a cosmological laboratory that clarifies Earth's beginnings and teaches us how to endure beyond it? Not as a stunt, not as a flag, but as a method, patient, engineered, and irreversible. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We move from crude validation to polar infrastructure and to a self-sustaining lunar economy. By the end, Artemis is revealed as a bridge between living systems and deep time, built one mission at a time. So Artemis III is reimagined for mid-2027 as an orbital validation mission that retires risk faster. Low Earth orbit is close enough for rescue options, rapid data return, and repeated attempts, which changes the psychology of testing. It is also harsh enough to expose integration failures that paper reviews cannot reveal, because vacuum, radiation, and thermal cycling do not negotiate. A lunar landing attempt bundles too many firsts into one irreversible chain, where one weak link can end the mission. In orbit, NASA can separate those firsts, test them repeatedly, and force the interfaces to prove themselves. This reorganization reframes success, and it does so in a way that feels almost countercultural. The headline becomes reliability, not a single dramatic touchdown, and that is a difficult story to sell. Yet the central question remains: how does Artemis become a permanent bridge to deep time science? That bridge depends on logistics, docking, transfer, and EVA, not on a single flag moment. It depends on the unglamorous ability to do the same hard thing again tomorrow, with the same result. Visually, the mission starts to look different in the mind's eye. Instead of a lone lander descending into black shadow, we see a busy orbital work site. Vehicles approaching, backing away, reapproaching, and exchanging mass like a slow, mechanical dance. The camera lingers on sunlight sliding across thermal blankets, on frost lines creeping along plumbing, on tiny attitude jets firing to keep a stack steady. In this version of Artemis, the drama is in discipline. Artemis III's core objective becomes operational choreography between Orion and a commercial lander stack. The mission tests rendezvous, approach corridors, hold points, and docking under strict flight rules, because proximity operations are where spaceflight becomes intimate. Relative motion in orbit is deceptive, and closing speeds that look gentle can still carry destructive energy. Docking is treated as a controlled collision, where alignment and timing decide whether structures survive. Interface standards matter because multiple contractors must meet at one ring in one geometry, with no room for interpretation. A millimeter-level mismatch can become a centimeter-level problem once loads shift and latches engage. Mechanical capture systems must tolerate small offsets without jamming, bouncing, or inducing rotation, because rotational energy can build faster than crews can react. Soft capture must damp relative motion before hard capture locks loads into the structure, and that transition is where surprises like to hide. Sensors are the real eyes, and their weaknesses become mission weaknesses. Cameras, LiDAR, and relative navigation filters must agree under glare, under shadow, and under the strange contrast of Earthlight reflecting off metallic surfaces. A docking target can bloom white in the sun, then vanish into a charcoal silhouette as the stack rolls. Failure modes are rehearsed because the first surprise in docking can become the last. Misalignment can shear seals, damage petals, or leave vehicles stuck in partial capture, where separation is harder than docking. A partial capture is a nightmare state. Loads are present, control authority is reduced, and the next command might worsen everything. Sensor dropout can create false closure rates, especially when lighting saturates optical trackers, or when a single star tracker loses lock. Software can mishandle a transient, commanding a correction that increases risk instead of reducing it, because control laws do exactly what they are told. Abort logic must be conservative, and it must be fast without being impulsive. It must detect divergence early and back away cleanly, using pre-planned corridors that avoid plume impingement and structural contact. The choreography includes human authority, and that is not a sentimental detail. Crews must know when automation is right and when it is wrong, because the last layer of safety is judgment under pressure. A safe approach is built from gates, and each gate is a deliberate pause in a universe that never pauses. Each gate forces a check, a go decision, and a confirmation that the system state matches the model. In Leo, those gates can be repeated across days, turning rare events into trained routines. The point is not to prove docking once. The point is to make docking boring, and boredom in space is often the sound of competence. Then Artemis III turns to the hardest quiet technology in the architecture: cryogenic propellant transfer. A scalable lunar program cannot rely on single launch landers with fixed tanks, because that approach collapses under its own mass fraction math. It needs refueling, aggregation, and redistribution, like a port that can stock and resupply, The idea is old in concept. Space stations were always meant to be waypoints, but new in execution at Artemis scale. Cryogenic transfer is hard because the propellants want to boil, stratify, and misbehave, and microgravity removes the comforting predictability of up and down. Liquid oxygen and methane or hydrogen sit near their boiling points, and space adds thermal extremes that swing with every orbit. Heat leaks through insulation, through valves, and through time itself, creating boil-off losses that cannot be wished away. Boil-off is not just wasted mass, and it is not just a number on a spreadsheet. It changes tank pressure, mixture ratios, and engine start margins. And those margins are what keep a landing from becoming a crash. A tank that warms unevenly can vent when you least want it to vent, and venting can impart tiny thrusts that slowly spoil attitude control. Thermal stratification forms layers, with warmer fluid above colder fluid, confusing sensors and models that assume uniform temperature. A temperature probe can read a stable number while the bulk propellant is drifting out of spec, because the probe is only touching one thin slice of reality. Slosh dynamics add another layer of uncertainty that engineers learn to respect. In microgravity, liquids do not settle. They float and oscillate, forming globules and sheets that move with every acceleration. During transfer, slosh can couple to vehicle attitude, inducing unwanted rotation and control effort, which then feeds back into the slosh. The system can feel almost alive, as if the propellant is arguing with the guidance system. Propellant management devices must guide liquid to outlets without ingesting vapor, using screens, vanes, and capillary forces that replace gravity's role. Vapor ingestion can cause pump cavitation, unstable thrust, or engine shutdown during critical burns, and those failures can be abrupt. Transfer lines must chill down because warm plumbing flashes cryogens into gas, spiking pressure and wasting mass. Even the soundless act of cooling a line becomes a choreography of valves, sensors, and patience. Leak detection becomes existential, and the danger is not always dramatic. A small leak can create an invisible cloud and an ignition hazard, and the cloud can drift into places no one intended. Hydrogen, in particular, can slip through materials that seem solid, while oxygen can turn ordinary surfaces into reactive ones. Sensors must distinguish a real leak from benign venting and from transient thermal contraction, because false alarms can be as disruptive as missed alarms. The mission tests seals, quick disconnects, and contamination control under repeated mate and demate cycles, because hardware degrades through use. A connector that works once is not a connector that can support a campaign. It also tests accounting, and accounting in microgravity is a science in itself. You must know how much moved, how much boiled, and how much remained usable, even when the fluid refuses to sit still. Without trustworthy gauging, planners cannot close the math on lunar sorties or sustained polar logistics. Gauging methods, pressure, volume, temperature models, mass flow meters, and thermal inference must be validated against reality, not just simulation. In LEO, NASA can instrument everything, iterate procedures, and refine the models that will govern lunar transfer. This is where Artemis becomes infrastructure. Transfer turns the moon from an expedition into a supply chain, and supply chains are what make presence durable. Artemis III also validates EVA as an integrated capability, not a dramatic walk outside. The Axiom U suit is tested during Earth orbit EVAs because suits are mini spacecraft, and many spacecraft can fail in miniature ways. They must provide pressure, oxygen, cooling, communications, and fault tolerance in a hostile vacuum, while still letting a human do delicate work. The suit's pressure is life, but pressure also fights motion, turning every bend into a mechanical negotiation. Mobility is a primary requirement, and it is measured in fatigue as much as in angles. Crews must bend, kneel, and work without exhausting themselves, because exhaustion becomes error. Joint torque, glove dexterity, and suit fit determine whether tasks are safe or slow, and slow tasks consume oxygen and cooling water. The life support backpack constrains everything, and its constraints are unforgiving. Mass, volume, and heat rejection limit endurance, and endurance limits science time. CO2 removal must stay stable during workload spikes. When breathing rates rise and margins shrink, thermal control must handle sunlight and shadow transitions that can change temperatures rapidly, especially when reflective surfaces turn into radiators. The suit must also support tool use, tether management, and translation along handrails, because a drifting astronaut is a problem that grows with every second. EVA procedures test human factors, and human factors are often where missions succeed or fail. Checklists, buddy checks, and emergency responses must be fast, and they must be memorable under stress. Communications loops must be clear, because a misunderstood call can waste minutes that no one has. A suit anomaly is not a maintenance issue. It is a countdown to loss of crew, and that reality shapes every decision. Dust mitigation is tested as a concept, even in LEO, where lunar dust is absent, because the solutions must be designed before the problem arrives. The goal is to validate coatings, seals, and cleaning methods that can resist abrasive contamination, and to see how they age with repeated handling. Lunar regolith is sharp, electrostatically clingy, and capable of destroying bearings and zippers. It is not beach sand. It is crushed rock that has never been weathered smooth, and it behaves like a slow, persistent, grinding paste. If dust control fails, habitat air becomes contaminated, and suit joints become short-lived. So Artemis III treats suit operations as a system, not a single piece of gear. Airlocks, umbilicals, and servicing flows are part of EVA, and they must be designed for repetition. The mission measures how long it takes to prep, egress, work, ingress, and recover, because time is the hidden budget. Those minutes become the real currency of lunar science, because sampling time is always limited. All of this connects back to cosmology, even if it sounds like pure engineering. Infrastructure precedes discovery, and history keeps proving the pattern. Telescopes needed stable mounts before they could change astronomy, and particle physics needed accelerators before it could rewrite matter. Without reliable transfer and EVA, the moon stays mostly unreachable, not in distance, but in practicality. Far-side radio arrays require delivery, assembly, calibration, and periodic repair. And repair is where dreams become commitments. They also require stable power and relay links, because the far side is quiet and isolated, shielded from Earth's radio noise. That quiet is precious, and it invites a question. What signals have we never heard because our planet is too loud? Polar sampling requires repeated sorties, deep drilling, and careful contamination control, because volatile chemistry is easily spoiled by careless handling. Long baseline observations require fixed points, precise timing, and instruments that do not drift. and drift is the enemy of subtle measurement. None of those dreams survive if docking fails, if propellant transfer is unreliable, or if suits cannot work. Artemis is building the method by which we learn our origins. The method must be repeatable, and repeatability is what turns a mission into a program. The moon's ancient light and dust do not yield answers to one-time visitors. They yield answers to sustained presence, where instruments can listen longer than any single crew. In that sense, Artemis is less like a sprint and more like the slow construction of an observatory, one interface at a time. It asks a quiet, unsettling question. Are we patient enough to build the tools that discovery demands? Artemis II in orbit is therefore not a detour. It is a protective constraint, chosen so that ambition does not outrun verification. It forces the lander stack, the transfer plumbing, and the suits to prove they can operate together. It creates a controlled environment where failure teaches instead of ending the story. And that is a rare luxury in exploration. It also changes the program's emotional rhythm, and the audience can feel the tempo slow. The doorway is still there, but the hand reaches carefully, testing the hinge before pushing through. The first new footprints are delayed so they can be permanent, supported, and scientifically useful. Once the landing system is proven in orbit, Artemis IV aims back toward the moon with sharper intent. The target is the South Pole, where shadows hide volatiles and geology preserves a deeper record. In oblique sunlight, crater rims glow while nearby floors remain black, and that contrast is more than visual. It is a map of temperature traps that may have held water ice for billions of years. That is the transition. Validation in Earth orbit becomes the key that unlocks the most provocative region. And the central question tightens again. Can this bridge carry us into deep time without breaking? Artemis IV arrives with a different promise than Apollo ever carried. It is not one landing, framed as a singular triumph. It is the start of repeatable access to a specific place, measured, scheduled, and designed to happen again. After Artemis II proved crewed deep space flight can be treated like a service, and Artemis III proved the landing stack can be trusted, the program finally commits to the surface. Early 2028 becomes the first human lunar surface return in over 50 years, and that gap matters. A generation has passed since Apollo's last ascent engine fired, and the moon has waited in silence. The mission is framed as infrastructure in motion, not a single heroic descent. In Apollo, the objective was to reach the surface quickly, do a burst of work, then leave. Artemis IV treats the surface as a node in a network, where each visit is a rehearsal for the next. The architecture begins by leaving Earth orbit and aiming for a working orbit around the moon. Orion carries the crew through translunar injection, cruise, and lunar capture, while systems quietly prove themselves in the dark. The goal is not to circle low and fast like Apollo. The goal is to enter near rectilinear halo orbit, then use it as a staging point. Visually, the shift is immediate. Instead of a tight, circular track hugging the lunar surface, the trajectory stretches into a tall loop that seems to lean. The moon turns beneath it like a slow dial, and the orbit's geometry keeps returning to familiar alignments. NRHO is an orbit shaped by the Earth and Moon together, not by the Moon alone. It is a three-body solution that loops high over one pole, then swings closer on the opposite side. The path looks odd because it is designed for stability and access, not for symmetry. In practical terms, NRHO sits near a gravitational saddle where forces partially balance. Small velocity changes can maintain the orbit for long periods, which is the quiet advantage behind the drama. That advantage becomes visible in propellant margins, in schedule flexibility, and in the number of second chances a mission can afford. Stability matters because station-keeping propellant is time, and time is science. NRHO can be maintained with relatively small corrections, compared with many low lunar orbits, where perturbations accumulate quickly. It also offers persistent line of sight to Earth for much of each orbit, which simplifies communications and navigation. That line of sight is not a convenience. It is an operational lifeline that keeps voice, telemetry, and timing coherent across vehicles, even when the surface is hidden. It also supports a relay role for surface operations near the poles, where terrain can block direct links. NRHO becomes a hub where logistics can queue, refuel, and depart again. The deeper reason is cadence. A polar campaign needs repeated arrivals, repeated departures, and predictable windows for rendezvous, because planning cannot be reinvented every time. NRHO provides a geometry that can be reused, so each mission does not rebuild its orbital math from scratch. It turns lunar space into a port where missions can stack rather than scatter. There is also a historical echo in that choice. Apollo's low lunar orbits were optimized for short stays and quick returns because the program's clock was political as much as technical. Artemis is optimized for endurance, and endurance begins with an orbit that behaves. From NRHO, the landing system takes over. SpaceX Starship HLS is the surface transport and temporary habitat for the first polar stay. Orion remains the return vehicle and the safe harbor in lunar orbit, steady and conservative by design. The crew transfers between vehicles, then commits to descent. The transfer is more than a hatch opening. It is a handoff between philosophies, from a capsule built for re-entry certainty to a lander built for surface utility. In the quiet choreography of checks and tethers, the mission crosses an invisible threshold. The descent is aimed at the lunar South Pole region, where sunlight is low and angles are unforgiving. Peaks can see near continuous light, while nearby crater floors never see the sun, even across geologic ages. This contrast is not just scenery. It is a temperature map that decides what can survive. From above, the terrain reads like a charcoal drawing. Ridges catch a thin, grazing glow, while adjacent basins collapse into blackness that cameras struggle to interpret. Shadows here are not temporary. They are permanent features, as real as rock. Permanently shadowed regions are cold traps. They sit at temperatures low enough to preserve volatiles for immense spans of time, often tens of kelvins above absolute zero. Water ice, carbon dioxide, ammonia, sulfur compounds, and organics can accumulate there, delivered by comets, asteroids, and solar wind chemistry. Once trapped, they can remain chemically legible. The term cold trap sounds simple, but it describes a powerful filter. Molecules that wander into sunlight can hop away because thermal energy lets them sublimate and migrate. Molecules that fall into shadow lose mobility, and the vacuum becomes a freezer that never cycles. Artemis IV's surface stay is planned around 6.5 days. That duration is short compared with a base, but long compared with a flag visit, and it changes behavior. It forces a real sampling strategy, not opportunistic scooping. It also forces an EVA cadence that can be sustained under fatigue. Time on the surface is a systems test disguised as geology. Each EVA requires suit prep, airlock cycles, comm checks, navigation, and tool management, all while dust clings and temperatures swing. A 6-day stay allows repeated loops of those procedures, which exposes bottlenecks and failure points. It also creates room for contingency days when something breaks. Contingency planning is not abstract at the pole. Lighting can be deceptive, shadows can hide hazards, and thermal gradients can stress hardware that looked fine in warmer tests. A missed timeline can cascade into missed samples, missed power windows, or reduced safety margins. The mission design treats schedule as a safety control. Even walking becomes a calculation. Low sun angles flatten contrast, so a shallow depression can look like solid ground until a boot sinks. The crew's situational awareness depends on careful scanning, deliberate pacing, and constant cross-checks with maps and instruments. Sampling at the South Pole is not like sampling warm regolith. The target materials can change phase quickly when disturbed, because vacuum rewards volatility with escape. Ice can sublimate into vacuum, and fragile compounds can be lost before they are even measured. The mission, therefore, treats sampling as a race against physics. Cryogenic soil and ice sampling begins with minimizing heat input. Tools must be designed to cut and capture without warming the sample, because friction and sunlight can be enough. Containers must be pre-cooled or insulated, and they must seal quickly. The goal is to keep volatiles in place, not to watch them vanish. In practice, that means short exposure times and disciplined choreography. A core is extracted, transferred, and sealed with motions that feel almost surgical, because every second is an experiment. The sample is not just material. It is a state of matter that must be preserved. Contamination control becomes a scientific requirement, not a bureaucratic one. Exhaust plumes, human breath leaks, suit outgassing, and lubricants can all add false signals that look like discovery. Even a small amount of terrestrial water or organics can corrupt isotopic ratios. Procedures must separate what was found from what was brought. The moon's surface is already chemically sparse, which makes contamination more dangerous. When background levels are low, a trace introduced by hardware can dominate the measurement, and the story becomes wrong. The mission's cleanliness rules are therefore part of the science instrument. The sampling chain must preserve context as well as chemistry. Crews document depth, stratigraphy, grain size, and thermal environment because location is part of composition. They track exposure time to sunlight and to cabin temperatures, since warming can fractionate volatiles. Without that metadata, a pristine sample becomes an ambiguous one. Volatiles are valuable because they carry isotopic fingerprints. Hydrogen isotopes can indicate whether water resembles cometary sources, asteroidal sources, or solar wind implantation, because each reservoir carries a distinct ratio. Oxygen isotopes can constrain mixing histories and processing, including how much material was altered after arrival. Nitrogen and carbon isotopes can hint at organic pathways and delivery mechanisms. Those ratios are subtle, but they are readable. A small enrichment in deuterium can point toward cometary contributions, while different signatures suggest carbonaceous asteroids or solar wind chemistry. The moon becomes a ledger, and isotopes become the ink. The question is not simply whether the moon has water. The question is where that water came from and what it says about Earth, whose oceans define habitability. If polar ice preserves a record of delivery, it becomes a proxy archive for the inner solar system's volatile traffic. It can reveal when water arrived, how often, and in what chemical forms. That record matters because Earth is a poor historian of its own beginnings. Plate tectonics recycle crust, oceans mix, and biology rewrites chemistry, so early signatures are overwritten or diluted. The moon is quieter, colder, and less altered, especially in shadowed traps. It can preserve a timeline that Earth erased. There is also the question of survival through violence. The early solar system was a place of frequent impacts, and the moon's surface records that history in cratered relief. If fragile volatiles persisted through that era, what does that imply about the resilience of the ingredients for oceans and atmospheres? Artemis II therefore ties survival to cosmology. Water is the immediate survival resource for future crews, but it is also a clue to how habitability emerges across worlds. The same molecules that can be mined for life support and propellant can also explain how oceans became possible. The doorway is practical and philosophical at once. The South Pole is also an operational proving ground for the program's shared risk language. Radiation constraints remain present, but the mission now adds terrain, dust, and thermal extremes that compound small errors. Dose budgets must be tracked across transit, orbit, EVA, and habitat time. Standards become real when they drive go or no-go decisions. Dust is part of that risk because it is both abrasive and electrostatic. It can work into seals, scratch visors, and degrade thermal surfaces that rely on clean radiators. Every contact with the regolith is a reminder that the moon is not inert, only airless. NRHO supports that discipline by simplifying communications and timing. Continuous links enable real-time monitoring of suit telemetry and environmental trends, including subtle changes in temperature and pressure. They also enable rapid coordination between surface crews, orbital assets, and Earth-based teams. A stable hub makes risk management repeatable. The mission's scientific logic depends on repeatability too. One set of samples can be intriguing, but it can also be anomalous, shaped by a local quirk. Multiple sorties allow cross-checks between craters, depths, and shadow regimes, which is how patterns emerge. Artemis IV begins the pattern, then future missions must confirm it. Even the 6-day stay is structured around this idea. Early EVAs prioritize reconnaissance and instrument placement, then later EVAs target deeper or more delicate sampling that demands confidence. The cadence builds from simple tasks to complex ones, while leaving margin for unexpected findings. The plan assumes discovery will disrupt the plan. That assumption is not romantic. It is a recognition that field science changes priorities, because the ground can contradict the map. When a sensor reads colder than expected, or a shadowed patch shows unusual texture, the schedule must bend without breaking. Artemis IV is also a rehearsal for turning a landing site into a work site. Crews must manage power, thermal control, consumables, and maintenance while doing science, because operations do not pause for curiosity. They must learn what breaks first when dust meets seals and when cold meets batteries. These lessons determine how quickly sorties can scale. The South Pole's darkness is not empty. It is a storage vault where molecules can wait for billions of years, protected from sunlight that would otherwise drive them away. If those molecules include organics, They become a chemical echo of early solar system processes. They also become a test of how common the ingredients of life might be. And the visuals reinforce the idea. A headlamp beam fades into black that never reflects, while a ridgeline glows faintly like a horizon at dusk. In that contrast, the moon feels less like a desert and more like a museum with locked rooms. This is where the central question tightens again. Artemis is building a permanent bridge between Earth and deep time, and the bridge must touch a surface that can answer. The polar volatiles are not just resources. They are a readable layer of history, preserved by cold and shadow. Artemis IV ends with a new definition of success. Success is not the first footprint, because footprints can be made once and forgotten. Success is returning with samples that still contain their most fragile truths, and with procedures that can be repeated. The moon becomes less like a destination and more like a laboratory that demands careful handling. To turn that laboratory into a working field station, the next step must add logistics and resilience. Artemis V brings more cargo, more redundancy, and the mobility to range farther from the first landing ellipse. The doorway widens when the supply chain becomes routine. Artemis V arrives in late 2028 with a quiet but radical promise, delivered in the language of schedules and checklists. The moon will no longer depend on one lander, one schedule, one failure tree. In the black sky above the South Pole, that promise feels almost abstract, until you picture a single valve stuck or one software patch delayed. Artemis IV proved humans can work the polar shadows without breaking the chain. Artemis V tries to make that chain resilient enough to repeat, even when hardware or politics slip. The difference is subtle on paper, yet enormous in practice, because repeatability is what turns a stunt into a system. The program's logic shifts from firsts to throughput, and that shift changes what counts as success. A lunar laboratory needs cadence, and cadence needs redundancy that planners can actually use. It is not enough to say there is a backup. The backup must be real, funded, tested, and ready when the primary path falters. NASA introduces competition inside Human Landing System, not as a slogan, but as risk control. A second provider reduces single-point dependency across engines, tanks, software, and supply lines. It also reduces the quiet fragility that hides in vendor tooling, workforce churn, and the long shadow of launch manifest conflicts. SpaceX's Starship HLS remains part of the plan, but it is no longer the only door. Blue Origin's Blue Moon Mark II joins as an operational alternative designed to land crew and carry cargo. In mission graphics, the two silhouettes look like different philosophies, one towering and expansive, the other compact and deliberate. This is not a beauty contest between silhouettes, nor a referendum on branding or spectacle. It is an architecture decision about how often crews can reach the surface and how often science can be repeated. The moon does not reward one perfect mission. It rewards the next mission that still launches after something goes wrong. Blue Moon. Mark II is built around liquid hydrogen and liquid oxygen, a propellant pair with a long pedigree in high-performance rocketry. Its BE-7 engine is optimized for deep throttling, precise landing control, and efficient performance in vacuum. Deep throttling matters near the surface, where a lander must hover, translate, and settle without kicking itself into instability. In vacuum, hydrogen and oxygen offer high specific impulse, which is a plain way of saying more useful push per kilogram carried. That efficiency buys margin, and margin buys options. Extra cargo, longer loiter, or a safer abort window. When the landing zone is ringed by shadows and slopes, those options become a kind of invisible safety gear. Hydrogen is difficult, and that difficulty is the point. Artemis is choosing to learn cryogenic discipline that will matter when propellant becomes a resource, not a shipment. The moon is cold in shadow and hot in sun, and both extremes conspire against a fuel that wants to boil away. Liquid hydrogen boils easily and leaks through small imperfections because its molecules are small and its temperature is unforgiving. Managing it forces better insulation, better seals, better chill-down procedures, and better accounting under time pressure. Even the act of loading propellant becomes a choreography of valves and sensors, one that must be repeated without improvisation. Cryogenic management is not just a tank problem. It is a systems problem that touches plumbing, avionics, and operations. Lines must be conditioned so propellant does not flash into gas, and vents must be controlled so ice does not form where it can jam mechanisms. In the polar environment, every plume and every vent can also loft dust, and dust has a long memory. Blue Moon's stated intent includes reuse, even if early missions treat it conservatively. Reuse is less about saving money than about stabilizing operations through repetition. When hardware returns to service, engineers learn what actually wears, what only looks worn, and what fails without warning. A reusable lander implies recurring inspection cycles, predictable refurbishment, and standardized interfaces. Those are the habits that turn exploration into infrastructure. In a hangar on Earth, reuse looks like a spreadsheet. On the Moon, it looks like a lander that can be trusted again. Blue Moon also brings a cargo delivery logic that complements crew landings, because crews cannot build a work site out of empty hands. If the surface is a work site, cargo must arrive ahead of people, and it must arrive reliably. A pallet of tools delivered on time can matter more than a headline, because it prevents the next EVA from becoming a salvage operation. Cargo is not glamorous, but it is the hidden enabler of science. Power units, spares, tools, and mobility hardware decide whether EVAs become discovery or mere survival. A missing connector can cancel a traverse as effectively as a storm, and on the Moon, the storm is often just dust and time. Hydrogen aligns with a long-term ISRU storyline, and the South Pole is chosen in part because it tempts that storyline. If lunar water ice can be harvested, electrolysis can split it into oxygen and hydrogen, creating a propellant loop. The chemistry is simple in principle, electricity in, gases out, yet the engineering is harsh. That loop is not immediate, and Artemis 5 does not pretend it is. The mission treats hydrogen as a rehearsal for the day the Moon supplies its own departures. Each cryogenic procedure becomes a small investment in a future where propellant is manufactured, stored, and transferred under lunar gravity. The central question tightens in a new way, because the Moon's distance is not measured only in kilometers from Earth. If the Moon is a doorway, the hinge is logistics, and logistics is measured in kilograms delivered and kilometers traveled. The hinge must move smoothly, again and again, or the door never truly opens. Artemis Vaithi's signature payload is mobility, and mobility is a statement about intent. The mission delivers the first lunar terrain vehicle, an unpressurized rover designed for repeated day trips. In the low-angle sunlight, its tracks and shadows will look almost theatrical, thin lines drawn across a landscape that has waited billions of years. The LTV changes the geometry of field science in a way Apollo only hinted at. Apollo crews walked and drove short distances, then returned to a single point with limited context. Even when Apollo had a rover, the mission cadence and communications of the era constrained how much systematic surveying could be done. With an LTV, the landing site becomes a hub, not a boundary. The crew can link scattered outcrops into one coherent geologic story. From above, the traverse lines begin to resemble a survey grid, and the moon starts to look less like a postcard and more like a field site. The rover is designed for manual driving and autonomous modes because polar terrain punishes distraction. Manual control supports improvisation in the field, while autonomy supports pre-planned routes and hazard avoidance. Autonomy can also hold speed and heading with a steadiness that preserves battery and reduces wheel slip. Autonomy is not a replacement for judgment, and the mission does not treat it as a magic trick. It is a way to reduce workload, protect timelines, and keep navigation stable when visibility collapses. When the sun skims the horizon, a shadow can erase a crater rim, and the rover must still know where it is. The LTV's practical range is often framed around 20 kilometers, a number that sounds modest until you map it on the ground. That number is not about adventure, it is about statistics and sampling confidence. A 20-kilometer radius multiplies the number of distinct places a crew can visit before the clock forces a return. A larger radius increases the number of distinct regolith units a crew can visit, which matters because lunar soil is not uniform. It reduces the chance that one local anomaly masquerades as a global pattern. In science, a single beautiful sample can mislead, while a set of ordinary samples can reveal the truth. Mobility also improves geologic context, which is the invisible scaffolding beneath every rock bag. Samples mean more when their source is mapped against stratigraphy, ejecta patterns, and surface age relationships. Context is what lets scientists argue about processes rather than just cataloging curiosities. Artemis II uses traverses to cross boundaries between regolith deposits, and those boundaries are often written in subtle textures. These boundaries can mark different impact histories, different mixing depths, and different exposure ages. A change in grain size or albedo can signal a different story, even when the landscape looks monotonous at first glance. Crater ejecta becomes a priority target because it excavates depth, acting like a natural drill that has already done the hard work. A fresh ejecta blanket can bring up material from layers, otherwise unreachable by hand tools. On the rim, boulders sit like torn pages from a buried book, waiting to be read. The rover allows crews to sample multiple ejecta rays and compare them across distance, rather than trusting one convenient outcrop. That comparison can separate local contamination from regional signatures, and it sharpens chronology. If one ray carries a distinctive mineral mix, the crew can test whether it fades with distance or persists across terrain. The mission also seeks potential paleoregolith layers, a phrase that sounds clinical but describes something fragile. These are ancient soil horizons, buried by later lava flows or impact deposits, sealed from ongoing space weathering. Finding them requires both luck and strategy, because they are revealed only where geology has cut a window into the past. Paleoregolith matters because it may preserve records of ancient solar activity stored in the quiet between events. Solar wind particles, cosmic ray tracks, and implanted volatiles can be trapped like a time capsule. In the lab, those trapped signatures can be measured with isotopic precision, turning dust into a timeline. Earth's atmosphere and geology erase much of that record through erosion, plate tectonics, and constant recycling. The moon's buried soils can store it, offering a proxy timeline for the sun's changing behavior. The idea is almost unsettling, an archive of radiation written into grains that have never known rain. That sun history is not an academic detail, because the sun is both a giver and a hazard. Solar activity shapes radiation risk, atmospheric loss, and the habitability trajectories of rocky worlds. When the sun was younger and more violent, it may have stripped atmospheres and altered surface chemistry across the inner solar system. Artemis V, therefore, links mobility to cosmology in a way that feels poetic and practical at once. A rover is a tool for reading deep time because it lets crews sample across space to infer time. Each kilometer traveled is a chance to compare surfaces that have been exposed for different durations under the same sky. The science plan becomes more like terrestrial fieldwork, where interpretation is built from relationships, not isolated finds. Crews can follow contact zones, revisit sites, and build a narrative that survives peer review. The LTV turns the crew into moving observers, not just stationary collectors. But the operational tension rises with every kilometer, and the moon is indifferent to optimism. The moon punishes moving parts, and a rover multiplies bearings, joints, seals, and failure modes. Every hinge is a question, and every wheel is a promise that must be kept under load. Dust abrasion is the constant enemy, because lunar regolith is not softened by wind or water. Regolith grains are sharp and electrostatically clingy, and they grind into wheels, suspension, and connectors. In Apollo, dust invaded suit joints and scratched visors, and Artemis inherits that lesson with more hardware to protect. The dust also behaves strangely in sunlight, levitating and clinging in ways that feel almost alive. It can coat radiators, darken thermal surfaces, and change how heat flows through a vehicle. A thin film can turn a carefully designed thermal balance into a slow drift toward overheating or overcooling. Thermal extremes add a second enemy, one that attacks materials at the microscopic level. Sunlit surfaces heat quickly, shadows drop toward deep cold, and hardware must survive repeated cycling without cracking. Metals expand and contract, polymers stiffen, lubricants thicken, and batteries lose performance when they are cold. Low sun angles at the pole create navigation traps that are more psychological than dramatic. Shadows stretch, contrast collapses, and a small berm can hide a wheel-breaking void. The surface becomes a study in grayscale, where the difference between safe and dangerous can be a few centimeters of relief. Navigation, therefore, becomes a layered system, because no single sensor can be trusted all the time. Crews use maps, inertial estimates, local landmarks, and rover sensors that must work under glare and darkness. The best navigation is redundant in method, not just redundant in hardware. Communications and timing remain part of the safety net, and they shape routes as surely as geology does. The rover must stay within link budgets and rescue timelines, because range without recovery is a mirage. A traverse plan is therefore also a communications plan, written in angles to relay assets and in minutes to spare. Power becomes the tyranny that shapes every plan, and it does so quietly, without drama. batteries define how far the rover can go, how long instruments can run, and how much margin remains for return. Every acceleration, every heater cycle, and every detour becomes a withdrawal from a finite account. Consumables planning ties directly to mobility because the crew is not separate from the vehicle. Oxygen, cooling water, and suit power must be budgeted against distance, workload, and contingency detours. A steep slope can cost more than time because it increases metabolic rate and heat load inside the suit. Every traverse becomes a negotiation between curiosity and margin, and that negotiation is the heartbeat of exploration. The crew must decide when a promising outcrop is worth the minutes it will steal. The most mysterious rock is often the one that appears late in the day, when the battery gauge is already speaking in warnings. Artemis II also tests how mobility integrates with the landing architecture, because the rover is not useful if it is fragile to handle. The rover must be deployed, checked out, maintained, and parked in ways that preserve future sorties. Even where it sits overnight matters, because shadows and slopes can turn a simple parking choice into a thermal problem. This is where redundancy becomes more than having two landers and more than a procurement strategy. Redundancy becomes a culture of interchangeable procedures, shared standards, and predictable logistics. When crews train, they train to a common language of risk, so that different vehicles still fit one operational rhythm. The program's common risk language, introduced earlier through radiation budgeting, expands into surface operations. Dust exposure, thermal cycles, and battery margins become tracked constraints. The result is a mission that feels less like improvisation and more like disciplined fieldwork under hostile conditions. Radiation remains in the background, shaping EVA durations and shelter rules even when it is invisible. Mobility changes exposure patterns, because longer traverses can extend time away from the lander. A rover can carry you farther, yet it can also carry you farther from the nearest shielding, and that trade never disappears. Artemis II therefore treats the rover as part of the habitat system, not merely a vehicle parked outside. It is transportation, but it is also a moving constraint that must fit the safety model. The rover's route planning becomes entangled with storm monitoring, return timelines, and the simple requirement to get home. Competition between landers supports this model by protecting cadence, which is the real currency of a sustained program. If one provider pauses for investigation or redesign, the other can preserve the rhythm of missions. That rhythm also protects the workforce and the supply chain, because long gaps are where skills fade and costs spike. That rhythm matters because science needs repetition, and repetition is how uncertainty shrinks. A single traverse can suggest a hypothesis, but repeated traverses across missions can confirm it. When multiple crews sample similar units at different times, the moon begins to yield patterns instead of anecdotes. The moon begins to feel less like a single landing site and more like a range, and a range implies choice. Range means the ability to choose targets, not just accept what is nearby. It also means the ability to return, to resample, and to test whether an earlier interpretation survives new data. Artemis II ends with a new kind of confidence, one built from systems rather than heroics. The program can deliver cargo, land with more than one system, and move far enough to build context. In the long polar twilight, the rover's tracks become a visible signature of that confidence. thin, temporary, and yet transformative. Yet the doorway is still only partly open, and the moon still keeps its distance. Day trips expand the map, but living requires staying power, maintenance, and the ability to work while moving. The questions become sharper. How do you repair a vehicle when dust has infiltrated everything? And how do you keep a schedule when the environment refuses comfort? If Artemis V turns scattered rocks into a coherent narrative, Artemis VI aims to turn that narrative into a routine. The next step is making the moon a place you can live while moving. Artemis VI, targeted for 2030, marks a pivot from sorties toward sustained mobile exploration across the lunar South Pole. The goal is higher science return per mission, measured in traversed kilometers, documented context, and the number of samples analyzed with clear provenance. Artemis IV proved the pole can be worked without breaking the chain, even when every step depends on timing and power. Artemis V expanded range with day-trip mobility and redundancy in landers, showing that contingency planning can be built into distance. Artemis VI asks a different question: can the crew live inside the traverse itself? The centerpiece is the pressurized rover, developed with JAXA as a mobile habitat that behaves like a small spacecraft. It is built to carry 2 crew and support up to 30 days of autonomous surface operations, including sleeping, hygiene, and routine maintenance. It is not a cart for tools. It is a sea-level atmosphere laboratory on wheels. Visually, the rover reads as a compact module with wheels and purpose, its body bright against charcoal regolith. Antennas angle toward a low horizon, while radiators and thermal blankets hint at the constant heat bookkeeping underneath. When it moves, it leaves a clean, deliberate track, like a signature written across ancient dust. Sea-level pressure and an Earth-like mix change the rhythm of work in a way that is both technical and human. Inside, astronauts can remove helmets, eat, sleep, and run instruments without suit constraints, and that comfort translates directly into precision. The rover becomes a moving field station that turns the surface into a traversable research campus. That atmosphere choice is not just about comfort, because pressure and gas composition govern decompression risk. When crews move between cabin and suit, nitrogen dissolved in the body can form bubbles if pressure drops too quickly. A rover that keeps a familiar pressure reduces how often that transition is needed, and it narrows the margin for error. The practical advantage is time, and Artemis treats time as the scarcest consumable on the surface. Every EVA demands suit checks, pre-breathe, airlock cycles, and dust management. And those steps are non-negotiable when lives depend on seals. A pressurized cabin reduces decompression cycles and cuts the overhead that steals hours from science. Apollo crews accepted that overhead as the price of first footsteps because the objective was to prove it could be done. Artemis is operating in a different era, where the question is not whether humans can work there, but how efficiently they can learn. Efficiency sounds mundane, yet on the moon, it becomes the difference between a single sample and a coherent story. The rover does not eliminate EVA, it makes EVA strategic rather than constant. Crews can drive for hours, stop briefly for targeted sampling, then retreat to shirt sleeves for labeling and preliminary checks. That loop reduces fatigue and preserves fine motor skill for delicate tasks like chip sampling, core handling, and clean bagging. Pressurization also protects equipment and people from constant suit wear, which is a hidden driver of mission risk. Suits are complex life support machines with joints that grind against dust, and lunar dust is sharp, electrostatically clingy, and persistent. Fewer hours in suits means fewer failures, fewer repairs, and fewer timeline collapses. The moon's dust earned its reputation during Apollo, when it abraded seals, irritated lungs, and worked into every hinge. In the harsh light, grains glitter like powdered glass, and in shadow they disappear into velvet darkness. Artemis 66 treats dust as an adversary that must be managed as carefully as oxygen. Human performance becomes a mission parameter, not a soft concern or a footnote. Long EVAs compound dehydration, thermal stress, and cognitive load under low contrast lighting, where shadows hide hazards and glare flattens depth. A pressurized rover gives recovery time that keeps judgment sharp across weeks. Inside the cabin, the visuals shift from stark exterior to controlled interior light, with checklists floating on screens and samples secured in labeled containers. A crew member can stretch, drink water, and review traverse maps without the constant hum of suit fans. That quiet matters, because sustained attention is a resource that can be spent too quickly. Artemis II's psychological unlock echoes here in a new form, even if the setting is different. The program learned to treat deep space living as routine through metrics, checklists, and calm decisions under delay, and routine is how anxiety is kept from driving errors. Artemis 6 extends that routine to the surface, where the environment punishes small mistakes. Radiation remains the invisible constraint that binds architecture together, even when the landscape looks still. A rover adds time on the surface, and time increases exposure to galactic cosmic rays that pass through skin and electronics alike. Artemis operationalizes a common risk language by tracking dose across cabin time, EVA time, and shelter time. That dose accounting is not abstract, because it shapes where the crew can go and how long they can stay. A few extra hours outside during a busy sampling day can change the allowable plan later in the month. The rover turns radiation into a managed variable, measured, forecast, and discussed like weather. The rover, therefore, carries shielding where it matters, plus procedures that matter more than material alone. Forecasting, storm response drills, and shelter rules become standardized across vehicles because solar particle events can arrive quickly. The same risk vocabulary used in Orion and NRHO now governs a moving habitat. Autonomy is framed as resilience, not convenience, because a long traverse is a long chain of small decisions. The rover must navigate polar terrain, manage power, and keep life support stable. During long traverses with limited external support, autonomy also protects the crew when visibility collapses and when fatigue would otherwise invite errors. The South Pole is not a flat plain, and the visuals emphasize that immediately. Ridges throw long shadows, crater rims rise like walls, and the sun skims the horizon as if reluctant to climb. A route that looks short on a map can become complex when slopes, boulders, and shadowed cold traps appear. Power and thermal control define the rover's real range because the moon is an extreme thermal machine. Batteries, solar input, and heater loads decide how far science can be pushed, especially when darkness can mean rapid cooling. Artemis 66 treats energy accounting as part of geology, because every detour is also a power decision. Thermal control is not simply comfort, because temperature affects batteries, lubricants, instruments, and even the brittleness of materials. In sunlight, surfaces can warm quickly, while in shadow they plunge toward cryogenic cold. The rover's radiators and insulation become as essential as its wheels. With mobility extended from hours to weeks, the science plan changes scale in a way Apollo could only hint at. Artemis II could connect nearby outcrops into a story, moving within a limited radius and returning to a fixed point. Artemis VI can connect distant provinces into a map of processes. The phrase "geography of discovery" becomes literal, and the camera can linger on that idea. A traverse line arcs across a terrain model, then resolves into real ground. Dust, rock, and subtle color changes in the regolith. Different terrains preserve different chapters of lunar history, and distance is the barrier between them. The pressurized rover makes that distance negotiable, but it also makes it accountable. Every kilometer is logged, every stop is time-stamped, and every sample is tied to imagery, orientation, and surrounding context. That discipline is how a traverse becomes a data set rather than a memory. Advanced geology becomes the mission's primary product, and it demands continuity. Crews can traverse across ejecta blankets, crater rims, and layered deposits while maintaining continuous context, because the rover carries the tools to record and compare. Context is the difference between a rock collection and a chronology. In practice, context means knowing not only what a rock is, but where it sat and what happened around it. Was it excavated from depth by an impact, or emplaced by a flow, or altered by micrometeorite gardening? The rover's mobility lets that question be asked repeatedly across multiple sites without rushing. Stratigraphy is the first target because layers are time-made visible in a landscape that rarely erodes. Impact ejecta, volcanic deposits, and regolith mixing create sequences that can be read if they are sampled systematically and mapped carefully. The rover enables that systematic approach across multiple sites. When the crew reaches a layered exposure, the visuals can slow down to show the geometry. A pale band cuts through darker material, and angular fragments sit embedded like fossils of violence. A handheld camera traces the boundary, while a sample bag receives a chip that represents a specific moment in lunar time. Crater counting is the second target, and it depends on calibration that only returned samples can provide. The moon's surface ages are often inferred by counting craters per area, because older surfaces accumulate more impacts. Those counts need anchor points from radiometrically dated samples, or the clock has no face. Artemis VI uses mobility to link crater statistics to ground truth, which is the core of the method. Crews can sample impact melts from specific craters, then tie those ages to the crater's morphology and eject a field. Each dated melt becomes a calibration point for the entire lunar surface. Impact melts matter because they record the violence that shaped early Earth's environment and the broader inner solar system. When an impact occurs, rock is heated, mixed, and reset in isotopic clocks, locking in a new starting time as the melt cools. If the melt can be tied to a known crater, the date becomes a timestamp in the bombardment record. That dating relies on predictable physics, and it is quietly elegant. Radioactive isotopes decay at known rates, and minerals can trap daughter products as they crystallize from melt. In plain terms, the rock becomes a stopwatch that started when it solidified. Refining that record is not lunar trivia, It is planetary context with consequences. The early solar system delivered impacts that influenced atmospheres, oceans, and the stability of early habitats, and those impacts were not evenly spaced. Earth's own early surface was erased by tectonics and weather, but the Moon kept the receipts. Historically, Apollo returned samples that transformed this debate, yet the coverage was geographically narrow. Those missions landed near the equator, and their traverses were short by necessity and by design. Artemis VI extends the sampling logic into new provinces, where polar geology and different impact histories can be compared. The rover's long duration allows repeated sampling strategies, not one-off grabs driven by the clock. Crews can revisit a site after preliminary analysis, then adjust targets based on what the first samples imply, which is how field science actually works. That feedback loop is how field science scales. The rover also supports instrument work that is hard during EVA, when gloves and time pressure distort fine tasks. In-cabin microscopes, spectrometers, and sample handling reduce contamination and preserve delicate textures that can be destroyed by rough handling. The cabin becomes a controlled environment in an uncontrolled world. A sample that looks ordinary outside can reveal its story under magnification inside. Tiny crystals show cooling rates, glassy veins show shock, and grain boundaries show later alteration by micrometeorite impacts. Those details guide the next drive because the traverse becomes adaptive rather than scripted. Dust control becomes a science enabler, not merely a maintenance chore that steals attention. Keeping samples clean preserves isotopic signals and exposure histories, because contamination can blur the very measurements that make a sample valuable. The rover's air management and filtration reduce the constant dust intrusion that plagued Apollo. The visuals of dust management are almost ritualistic, and that is the point. Brushes, air curtains, and careful bagging become part of the choreography, while seals are inspected with the seriousness of surgery. On the Moon, cleanliness is not aesthetic, it is epistemology. Artemis VI also expands the search for buried records of the Sun, which are subtle and easily overlooked. Paleoregolith layers, sealed between lava flows or ejecta, can store solar wind and cosmic ray signatures like a tape recording. Reaching them often requires moving far enough to find natural exposures, where layers are cut open. Those exposures might appear as a cliff face in a crater wall or as a fresh scarp where impacts have sliced the ground. In the low sun, the texture of the layers becomes visible and the boundary lines sharpen. The crew is not just collecting rocks, they are collecting time-stamped radiation history. Those solar signatures connect the Moon to cosmology-adjacent questions, even though the samples are small. The Sun's early activity shaped atmospheric loss and surface chemistry on rocky worlds, and it likely influenced how water and volatiles behaved. A better solar history improves models of habitability, including why Earth remained hospitable. The impact chronology and the solar history converge in the same archive, which is why the Moon is so scientifically powerful. Impacts churn the regolith and reset surfaces, while solar particles implant and alter grains over long exposure. Understanding both processes improves how scientists interpret what the Moon preserved. This is where the central question tightens again, and the narration can lean into the mystery. Artemis is turning the Moon into a cosmological laboratory by making its records reachable and repeatable rather than rare and anecdotal. Mobility is the method that converts ancient dust into testable timelines. Artemis VI treats the lunar surface as a campus with routes, stations, and planned revisits, even if the buildings are made of rock and shadow. The rover makes distance a schedule item rather than a barrier, and that changes how questions are framed. Science return becomes a function of how intelligently the crew can move. The mission also reframes what a landing site means, because the center of gravity shifts. A lander is no longer the center of the world. It is a node in a network of traverses and return paths. The rover makes the node mobile, and mobility changes what can be asked. Operationally, the rover is a bridge between exploration and planetary science at scale, and that bridge is built from procedures. Exploration is reaching a place and surviving there, often by improvisation under stress. Science at scale is comparing places until patterns emerge, and patterns require consistency. The comparison is what makes the moon a doorway rather than a destination, because it turns local observations into a system-wide narrative. If Artemis can date surfaces, calibrate crater counts, and read solar history, it can reconstruct early solar system dynamics with improved confidence. Those dynamics feed models of planet formation and long-term habitability. The stakes rise because the questions become less local and more universal, even if the work looks like careful sampling. When the bombardment timeline sharpens, it constrains how often Earth-like worlds endure sterilizing impacts during their vulnerable early phases. When solar evolution sharpens, it constrains how often atmospheres survive, long enough for complexity to emerge. Artemis VI therefore makes a quiet claim about method, and the claim is deliberately unglamorous. The program is not chasing a single spectacular discovery. It is building the ability to make many discoveries reliably across time. Reliability is what turns mystery into knowledge. Yet mobility alone does not make a settlement, and Artemis does not pretend otherwise. A rover can extend reach, but it still depends on power, spares, and safe havens, and those dependencies are unforgiving. Without sustained energy and fixed habitats, each traverse remains an expedition. The transition is unavoidable because endurance has a ceiling when everything is carried and nothing is produced. To keep the moon as a working laboratory, Artemis must move from mobile endurance to permanent presence, where systems can be repaired and upgraded in place. Artemis VII, through IDs, will focus on power systems, habitats, and the logistics that make weeks become seasons. The doorway widens again when movement is no longer borrowed time and when routes can be driven as routinely as supply lines. The next chapters build the infrastructure that lets the rover's routes become routine, and routine is what makes science cumulative. Only then does the moon become a permanent bridge between Earth and deep time. Artemis VI proved you can live inside the traverse, but only on borrowed time. Artemis EC through Aethons shift the story from missions to settlement because science needs seasons. The camera language changes with them, less countdown, more calendar, because the moon finally becomes a place where tomorrow matters. The central question tightens at the South Pole, where the moon's archive becomes reachable. In oblique sunlight, crater rims glow like knife edges, while their interiors stay black for billions of years. How does Artemis turn this airless threshold into a cosmological laboratory, not a campsite? A permanent foothold changes what counts as success and what counts as failure. cadence, reliability, and maintainability begin to matter more than any single first. In the background, a quieter metric takes over. How many problems can be solved without calling Earth a rescue plan? Apollo could afford heroics because the goal was proof and return. Artemis must afford repetition because repetition is how uncertainty shrinks into knowledge. The moon is not forgiving, yet it is consistent, and consistency is what experiments and settlements can exploit. The program's new unit of progress is not a landing, but an operational rhythm. Cargo arrives, power stays on, life support closes loops, and repairs happen without drama. When the rhythm holds, the base stops feeling like a visit and starts feeling like a system. Artemis 7th, targeted for 2031, is framed as the true return to the moon. It expands Artemis Base Camp with the first durable habitat elements and surface utilities. Visually, it is less about a single descent plume and more about cranes, pallets, and careful placement on uneven regolith. Artemis VIII, targeted for 2032, follows as reinforcement rather than escalation. It adds capacity, redundancy, and the first power architecture meant to run unattended. The point is not to impress the audience, but to reduce the number of ways a single failure can end a season. These missions are less cinematic than a flag, yet more consequential than a footprint. They decide whether the moon becomes a lab that can keep promises. A footprint is evidence of arrival, but a working habitat is evidence of intent. The foundational surface habitat becomes the anchor of Artemis Base Camp. It is designed for 4 crew and roughly 60 days of continuous occupancy. In wide shots, it sits low against the horizon, its geometry purposeful, rounded where pressure pushes, layered where impacts and radiation threaten. 60 days forces a different kind of engineering honesty than a week. Every leak, filter, valve, and software timer must survive boredom as well as emergencies. Small degradations matter because slow failures are the ones that hide behind routine until they become irreversible. Life support shifts from open-loop consumption to managed recycling with clear failure modes. Oxygen generation, carbon dioxide removal, humidity control, and water recovery become daily operations. In plain terms, the habitat must behave like a small, sealed ecosystem that is constantly audited. Oxygen generation is not just a tank, it is chemistry and control. Electrolysis splits water, compressors shape pressures, and sensors watch for drift that humans cannot smell. Carbon dioxide removal is equally procedural because sorbent beds saturate, regenerate, and eventually wear out under real cycles. The habitat's air is not just breathable, it is measurable and accountable. Sensors track trace contaminants, microbial load, and partial pressures that drift under real use. A closed volume amplifies tiny sources, off-gassing plastics, cleaning agents, even human metabolism. So the base must measure what it cannot intuit. Water is treated as both consumable and thermal tool because heat is always the hidden budget. The habitat must move heat to radiators without letting dust cripple them. In the cold shadow, waste heat becomes survival, while in sunlight it becomes a problem that must be exported. Thermal control on the moon is brutal because there is no air to soften extremes. Heat moves by conduction through structure and by radiation to space, and both paths are unforgiving. A radiator that is slightly fouled, slightly shaded, or slightly misangled can change the internal temperature story. Micrometeoroid shielding becomes a design requirement, not a safety margin. The Moon's surface is a shooting gallery of tiny impacts that never stop. Most are smaller than sand grains, yet at orbital speeds they behave like bullets, punching pits and spall into anything exposed. Radiation strategy also stops being a briefing slide and becomes architecture. The habitat needs a storm shelter volume, dose tracking, and rules that crews can execute. Solar particle events can arrive fast, and the difference between inconvenience and injury can be measured in minutes. This is where the common risk language matures across vehicles and surface systems. Dose budgets link Orion transit, surface EVA, rover time, and habitat sheltering into one ledger. The base turns radiation from an abstract hazard into a managed resource. Time outside becomes something you spend. Artemis II's psychological unlock echoes here in a quieter form. Crews trust the system because metrics, drills, and incident responses have become repeatable services. Confidence is not bravado. It is familiarity. Knowing which alarm matters and which one is a sensor that needs cleaning. Dust control becomes existential because permanence means accumulation. Airlocks, suit ports, brushes, electrostatic mitigation, and filtration are treated like life support, not housekeeping. In close-up, regolith clings like charcoal powder, embedding into fabric weaves and scratching any surface that tries to resist it. Regolith is abrasive and clingy, and it attacks seals, joints, optics, and lungs. A base that cannot control dust becomes a base that cannot keep operating. Apollo crews described it as smelling like spent gunpowder, but the real issue is mechanical. Dust turns every moving part into a slow grinder. The airlock becomes a laboratory of its own, with choreography and discipline. Suits are isolated, surfaces are wiped, and filters are monitored like medical devices. Every step is mundane, yet each step prevents the base from becoming a long-term contamination experiment. Thermal control becomes equally existential once you stop leaving after a few days. The habitat must survive long, cold soaks, hot sun angles, and cycling that cracks materials. The Moon's day-night rhythm is slow, but the stress it imposes is persistent, and persistence is how fatigue wins. Power is the hinge that makes every other promise real, and Artemis stops pretending solar is enough. At the poles, sunlight is angled, intermittent, and terrain shadowed. The most valuable real estate is not flat ground, but high ground, ridges that see the sun longer and the shadows less. Solar arrays can work, but they demand towers, careful placement, dust cleaning, and energy storage. Batteries sized for long darkness become heavy, complex, and fragile to temperature. Even when the sun returns, a cold-soaked battery can refuse to deliver its rated performance without careful warming. Away from the poles, the 14-day lunar night is a hard wall for solar-only living. If power dies, heaters die, and a habitat becomes a freezer full of broken systems. The physics is simple. Without continuous energy, water lines freeze, lubricants thicken, and electronics drift outside safe limits. Fission surface power enters as the unglamorous solution that enables permanence. Around 40 kilowatts of continuous electricity turns survival into scheduling. It is the difference between living by the sun's permission and living by a plan that can be kept. Constant power means constant thermal control, stable communications, and predictable life support. It also means instruments can run continuously instead of only when the sun cooperates. In the visuals, the base stops blinking on and off like a campsite and starts glowing steadily like a small, distant city. Fission power changes logistics because it reduces the number of emergency modes. Instead of planning around darkness, crews plan around maintenance windows and spares. That shift is subtle, yet it changes the psychology of the place. Work becomes proactive rather than defensive. The reactor is not treated as a symbol, but as a machine with procedures. Deployment distance, shielding geometry, monitoring, and safe shutdown become routine checklists. It sits apart from the habitat, connected by cables and policy, close enough for service, far enough for prudence. With power stabilized, the base begins to behave like an ecosystem of interdependent subsystems. Habitat, rover, comms, science instruments, and ISRU prototypes share the same grid. A fault in one branch becomes a diagnostic story, not a catastrophe, because the grid is designed to isolate and recover. Operational ecology becomes the story, because nothing stays new on the moon. Maintenance EVAs are scheduled like experiments, and experiments are scheduled like maintenance. The calendar fills with inspections, filter swaps, connector cleanings, and software updates that must be tested as carefully as any new payload. Spare parts become as important as payloads, because failure is not a surprise. Artemis builds a catalog of wear items, swap procedures, and connectors standardized across vendors. Standardization is not glamorous, yet it is how you avoid a base full of incompatible bolts and orphaned cables. Autonomy grows from convenience into necessity as crews stay longer. Systems must detect faults, isolate leaks, and protect themselves while humans sleep or work outside. The base learns to watch itself, trending pressures, temperatures, and power draw, so that small anomalies are caught before they become narratives. Communications also become infrastructure rather than event support. Relay assets, local networks, and time synchronization keep the base coherent under light-time delays and terrain masking. Even a few seconds of delay changes how you troubleshoot because you cannot rely on real-time coaching when a valve sticks. This is where the two-lander strategy pays off in a new way. Redundancy is not just landing insurance, it is schedule insurance for cargo and crew rotation. The base is fed by a chain, and chains fail when any single link becomes a single point of waiting. If one lander stands down for investigation, the other preserves cadence. Cadence preserves the supply chain, the trained workforce, and the scientific continuity that makes data comparable. Long-term datasets demand stable methods, same calibration habits, same sampling protocols, same timing discipline. A base also forces a new philosophy of packaging and interfaces. Cargo must be modular, serviceable in gloves, and designed for reuse instead of single mission disposal. In practice, that means handles you can grab, latches you can trust, and connectors that tolerate dust without becoming permanent. The logistics rhythm becomes predictable by design. Regular flights deliver food, spares, instruments, and upgraded modules, while returning samples and failed parts for forensics. The surface begins to show the marks of routine. Paths compacted by rover wheels, staging zones, and labeled storage that looks almost terrestrial. That return stream matters because it closes the learning loop. Hardware that breaks on the moon teaches more than hardware that never leaves a clean room. Back on Earth, engineers can cut it open, read the wear patterns, and translate lunar reality into the next revision. As the rhythm stabilizes, a lunar economy begins to appear, almost accidentally. Transport, power, water, and data become commodities that can be priced and traded. It is not a sudden marketplace, but a gradual recognition that services can be measured, metered, and improved. Transport becomes a service with performance metrics, not a bespoke adventure. Kilograms to surface, kilometers of traverse support, and hours of power delivery become contractable outputs. The language shifts from heroic to actuarial. Reliability percentages, turnaround times, and cost per delivered capability. Power becomes sellable because it is divisible and metered. A science package, a comms node, and an ISRU skid can each buy watts and schedule their operations. Once electricity has a price, efficiency becomes a form of exploration, because every saved watt can be spent on another measurement. Water becomes the most strategic commodity because it is both life support and propellant feedstock. Ice prospecting, extraction, and purification become the base's economic gravity. At the South Pole, that water is locked in darkness, mixed with regolith, and protected by cold that never relents. Data becomes a commodity because continuous observing produces continuous archives. Bandwidth, storage, and processing become part of the base's value, not just its documentation. A steady stream of calibrated data is what turns a site into a reference point, and reference points are what science builds upon. This is also where the moon becomes an instrument platform, not just a place to stand. Long-lived outposts can host long baseline experiments that require stability and time. The surface becomes a foundation for measurements that cannot be rushed because the signal is smaller than the noise of a single mission. Seismometers improve with years of listening, not days of deployment. A persistent network can map the moon's interior and refine models of its formation and cooling. Each moonquake, each impact, and each thermal crack becomes a probe. Waves traveling through layers that reveal density, fractures, and history. Radio astronomy benefits from the moon's quiet and from fixed geometry. Arrays can be expanded over multiple missions, calibrated repeatedly, and protected by routine maintenance. The far side is famously shielded from Earth's radio chatter, but even near-side arrays gain from stable baselines and predictable interference environments. Optical and infrared observing campaigns gain from continuity and thermal stability. Instruments can observe through many lunar days, building datasets that survive statistical scrutiny. With careful shielding and steady power, detectors can be kept at stable temperatures, which reduces noise and makes faint signals less ambiguous. Long baselines also enable precise geodesy and fundamental physics tests. Stable stations separated by kilometers can measure subtle motions and validate models of lunar dynamics. Over time, tiny shifts, tides, thermal expansion, and the moon's slow wobble become measurable, and measurement is how models earn trust. Cosmology enters through method rather than spectacle. The moon becomes a platform where ancient light and ancient dust are measured with patience, not just collected. The romance is still there, but it is quieter. An archive read line by line, with instruments that must remain honest for years. Permanence changes the questions crews can ask on the surface. Instead of what is here, the question becomes what is consistently here and what changes over time. In a place with no weather, even small changes matter, because they are often the signature of deeper processes. It also changes what answers can be verified. Repeat sampling, repeated instrument calibration, and repeated traverses turn hypotheses into results that can be defended. What looks like a discovery on day 5 might be a bias, but what holds on month 5 starts to look like truth. Artemis Base Camp therefore reframes exploration as a controlled experiment in living off-world. The base is both laboratory and subject, measuring how humans endure beyond Earth. Every log entry becomes data: sleep quality, maintenance time, consumables, and the subtle frictions of isolation. Yet permanence also raises the stakes, because a base concentrates risk. A single dust failure, a single power anomaly, or a single logistics gap can cascade across everything. The moon's silence makes those cascades feel sharper. No wind, no rain, just the sound of fans and the knowledge that they must keep spinning. That is why maintainability becomes the program's hidden drama. The real cliffhanger is whether crews can fix what breaks, with the tools and time they actually have. A wrench that slips in a glove, a connector that cross-threads, a software patch that fails. These are the moments that decide permanence. By Artemis 9 and X, the base is treated as upgradable rather than finished. New modules add volume, redundancy, and specialized labs that reduce dependence on Earth analysis. The base begins to look less like a single habitat and more like a clustered campus with clear zones for living, work, and power. By Artemis II, the narrative is no longer about arriving, but about staying without constant rescue posture. The moon begins to feel less supplied and more self-supporting. The question becomes almost philosophical. What does it mean to live somewhere that cannot forgive improvisation? The transition point is ISRU because it changes the direction of dependency. Once you can live and power systems reliably, the moon stops being supplied by Earth. That inversion is the hinge of the chapter. When local matter starts to replace imported mass, the map of possibility redraws itself. USRU begins modestly, with oxygen production tests and water handling that prove plumbing discipline. The goal is not independence overnight, but verified closure of key loops. Early systems are prototypes by design, and prototypes are valuable because they fail in ways that teach you what to harden. Electrolysis turns water into oxygen and hydrogen, but only if power and cryogenic management are real. The polar environment tests boil-off, leaks, storage, and transfer under dust. Hydrogen is especially unforgiving because it is small, it escapes through tiny imperfections, and it demands careful materials choices. Every kilogram produced locally reduces the tyranny of launch schedules. It also creates a market signal that attracts more hardware designed to use local resources. Once production is measurable and repeatable, investment follows, because the moon stops being only a destination and starts being a supplier. Artemis 7th through Isine therefore build a bridge between two futures. One future is a sustained lunar laboratory that answers deep time questions with continuous measurement. The other future is a lunar economy that makes that laboratory affordable by changing what must be shipped. The doorway widens when the moon begins to supply itself. That is not a slogan. It is a logistics equation. Mass saved becomes capability gained, and capability gained becomes more measurement. The base becomes a feedback loop where infrastructure enables science, and science justifies more infrastructure. The mysterious promise is simple and severe. If Artemis can keep power on, keep air clean, and keep systems repairable, the moon becomes a permanent bridge to deep time. And if it cannot, the moon will not punish with drama. It will simply outlast the plan. Next, the program must prove that local resources can feed that bridge. The moment ISRU becomes routine, Artemis stops being a campaign and becomes a civilization experiment. The question that lingers is not whether humans can touch the moon again, but whether they can keep a promise there, quietly, repeatedly, for years. The moon becomes a doorway only when it can feed the people crossing it, and Artemis is finally close to that reversal. Habitats, power systems, and mobility exist now, yet every kilogram still begins on Earth with a price tag in risk. Chapter 9 is the inversion point, where local ice becomes air, fuel, and a new kind of evidence. ISRU is first framed as survival math, not futuristic romance, because arithmetic is what keeps crews alive. Water is mass, and mass is launches, and launches are schedule risk that compounds with every delay. Every extra tanker flight adds weather windows, docking events, and failure modes that cannot be wished away. If water can be made on the moon, the base stops living on borrowed time and starts living on its own balance sheet. Artemis 9 through Ainis treat ISRU like industrialization under laboratory rules, where curiosity is allowed but surprises are not. Early units are pilot plants, designed to fail safely and teach quickly, with sensors everywhere and margins built in. The scale-up logic is explicit because multi-ton production is the threshold between demonstration and infrastructure. It is also the point where a plant stops being an experiment and becomes a utility, like power or air. A kilogram-per-day rig proves chemistry can run once, under ideal attention and controlled inputs. A ton-per-month rig proves plumbing, seals, maintenance, and spares can survive real cycles, including thermal swings and abrasive dust. Multi-ton output proves the base can plan around production, not around luck, and planning is what turns a camp into a settlement. That is why Artemis treats output curves like medical charts. Trends matter more than a single good day. The program defines a simple economic truth that sounds cold, yet it is deeply human. Propellant is the currency of deep space because it buys time, abort options, and reach when plans break. Delta V is not just physics, it is freedom. Freedom to leave, to return, to try again. If the moon can mint propellant, the architecture of exploration changes shape, and the map of what is practical redraws itself. The chain begins with prospecting, because you cannot refine what you cannot map with confidence. Orbiters and surface assets use neutron spectrometry to infer hydrogen abundance across shadowed terrain. Cosmic rays strike the regolith and knock neutrons free, and those neutrons carry information as they scatter upward. Neutrons slowed by hydrogen become a proxy for buried ice, even when sunlight never reaches it. In visuals, the data becomes a ghostly heat map, draped over crater rims and black interiors. Bright patches of inferred hydrogen cling to permanent shadow like frost that cannot be seen directly. The map is never perfect because resolution is limited and the signal integrates depth. Artemis therefore treats every pixel as a probability statement, not a promise, and that humility shapes the next steps. Ground-penetrating radar adds geometry to that proxy, and geometry is what drills and excavators need. Radar pulses penetrate the subsurface and reflect from boundaries where electrical properties change. It can hint at layering, blockiness, and dielectric contrasts that suggest ice mixed with regolith or lenses trapped between drier layers. The goal is not a pretty map. It is a drilling plan with quantified uncertainty, including what might go wrong. Prospecting is also a contamination problem from the first measurement because the act of arriving changes the site. A rover wheel can loft dust into a cold trap, and dust can carry terrestrial water from breath, coolant, or exhaust. Even a warm instrument box can create a microclimate that nudges volatile molecules into motion. Artemis writes strict keep-out zones and approach corridors, then treats violations like lost science, because that is exactly what they are. The next link is excavation in cryogenic regolith, where the moon stops behaving like a normal work site. At tens of kelvins, volatiles are stable, but machinery is brittle, and lubricants misbehave in vacuum. Metals contract, polymers stiffen, and ordinary greases can evaporate or freeze into useless wax. Every moving joint becomes a risk register entry, and every hinge is a place where the moon tests engineering pride. Excavation is designed to minimize heating, because heat is loss, and loss is irrecoverable. Warm regolith releases volatiles before capture hardware is ready, and in vacuum, they do not politely wait nearby. The system must move cold material into sealed volumes, then control temperature rise like a medical dose, slow enough to manage, fast enough to be useful. In imagery, scoops and augers work under stark floodlights, their shadows razor-sharp against black sky. Thermal processing follows, and it is the first true alchemy step that turns dirt into breath. Regolith is heated in ovens or reactors, driving off water and other volatiles as gases. Some designs bake the soil in batches, while others feed it through continuously like a conveyor furnace. The process must be power accounted because each watt competes with life support and science, and the pole's energy budget is never infinite. Capture hardware then faces the moon's most unforgiving constraint, which is emptiness itself. In vacuum, gases do not linger, they escape, and diffusion becomes a race against open space. Cold, traps, condensers, and getters must intercept molecules quickly before they vanish into darkness. Surfaces are engineered for sticking probability, and flow paths are shaped to avoid dead zones where vapor can hide. The plant becomes a choreography of pressure, temperature, and timing. Purification is where the pilot plant becomes a chemical factory, and where small impurities become big consequences. Water must be separated from CO2, sulfur species, and organics that can poison catalysts or foul membranes. Trace compounds matter because electrolysis stacks and cryogenic valves are unforgiving about contamination. Filters, membranes, and distillation steps must work under dust, vibration, and thermal cycling, and they must be serviceable by tired hands in bulky gloves. Storage is the quiet cliffhanger because the products are hard to keep even after you have won them. Liquid oxygen is manageable but still demanding because it boils away if insulation or refrigeration slips. Liquid hydrogen is a leak-seeking, boil-off-driven adversary that punishes tiny imperfections and exposes every weak weld. Hydrogen molecules are small enough to permeate materials, and embrittlement can make metals crack over time. On screen, frost creeps across tank lines like a living thing, and gauges become the only calm voices. Artemis 5 rehearsed hydrogen handling as a promise, but Artemis 9 makes it a ledger with consequences. tanks are weighed, pressures trended, and losses measured over weeks, because days are not enough. The question is not can we store hydrogen, but can we store it predictably under lunar cycles? Predictability is what allows mission planners to write numbers into timelines without crossing their fingers. Electrolysis is the hinge reaction that turns water into two strategic gases, and it looks simple until it is not. Electricity splits H2O into hydrogen and oxygen, but efficiency depends on temperature, purity, and electrode health. Oxygen becomes breathing air and the oxidizer that most rockets actually burn, because oxidizer dominates propellant mass. Hydrogen becomes the other half of high-performance propellant and the hardest half to keep, move, and measure without loss. Oxygen for breathing closes a life support loop and reduces resupply mass, which reduces the number of launches that must go right. Oxygen for engines changes the logistics equation more dramatically because ascent, rendezvous, and abort burns are dominated by oxidizer mass. The base can tolerate many inconveniences, but it cannot tolerate running out of oxidizer at the wrong time. That is why oxygen production is treated like a safety system, not a convenience. When oxygen is made locally, landers can arrive with less dead weight and more payload flexibility. When both oxygen and hydrogen are made locally, the moon becomes a refueling node, and nodes change networks. That is why multi-ton production is treated as a program-level milestone, not a technical trophy. A node means you can stage missions differently, carry more margin, and recover from mistakes without spending a year rebuilding supply. Artemis II is positioned as the first integrated extraction chain test, and integration is where optimism usually breaks. It links prospecting data to a chosen dig site and runs end-to-end for days, with every step logged. The success metric is not peak output, it is stable operation with known failure modes and bounded losses. Engineers want to see graceful degradation, what happens when a heater underperforms or a valve sticks halfway. Artemis X pushes scale and autonomy because crews cannot babysit a plant forever without paying in fatigue. The system must detect leaks, isolate faults, and recover from trips without human panic or constant intervention. Control software learns the difference between a transient and a trend, and it learns when to shut down. This is where the common risk language expands from radiation into chemistry, and from chemistry into operations discipline. Artemis VIII aims at multi-ton class output, even if only briefly, because brief success still exposes real constraints. That threshold forces industrial choices, including redundancy, modular replacement, and standardized interfaces that can be swapped quickly. It also forces policy choices, because contamination rules become harder to enforce at scale and under schedule pressure. A bigger plant has a bigger footprint, and footprints are how pristine places become ordinary. The tension sharpens around the cold traps themselves, which are both resource and archive, and those roles collide. They are the most pristine places Artemis can reach, with temperatures so low that molecules can remain trapped for eons. They are also the easiest places to ruin with exhaust, dust, or a single spilled tank that flashes into vapor. One careless vent can rewrite a local chemical record, and no apology can restore it. NASA treats contamination as a scientific crime, not a public relations risk, because the evidence is fragile. Landing plumes can loft regolith and migrate volatiles, and the lofted grains can travel farther than intuition suggests. Even a small change in local temperature can mobilize molecules that were stable for billions of years. The moon's quiet is deceptive. Small disturbances can have long tails. So Artemis separates industrial zones from sampling zones, then audits that separation as if it were a flight-critical system. It uses witness plates, blanks, and isotopic tracers to detect terrestrial signatures, and it does so repeatedly. It logs every thruster firing and every vent, because metadata becomes part of truth when chemistry is the witness. The record is meant to survive skepticism, including skepticism from future scientists who were not there. The mystery is that lunar ice is not just water. It is a story about where water came from. Isotopic ratios become the language of that story because isotopes preserve origin clues through time. D/H and oxygen isotopes act like fingerprints that survive long after impacts and burial. In the lab, a ratio is just a number, yet on the moon, it becomes a narrative constraint. If D/H matches certain comets, it suggests delivery from the outer solar system on long, cold arcs. If it matches carbonaceous asteroids, it implies a different transport path through the inner solar system's mixing zone. If it trends towards solar wind values, it suggests the moon is manufacturing water in place, grain by grain. Each match is a different history of bombardment, migration, and chemistry. The program must distinguish ancient deposits from modern implanted hydrogen, because both can exist in the same crater. Solar wind protons can embed in grains and react with oxygen in minerals, forming hydroxyl and water at the surface. That process can create water signatures that look real, yet represent recent surface chemistry rather than ancient ice. The moon is both a freezer and a factory, and the data must say which is speaking. Depth profiles become the discriminator, and depth is a kind of time axis in frozen ground. Ancient ice should show stratigraphy, shielding, and isotopic consistency with burial time, even if mixed by impacts. Modern implanted hydrogen should concentrate near the surface and correlate with exposure history and micrometeorite gardening. The drill, therefore, becomes an instrument of chronology, not just of extraction. Artemis crews, therefore, treat drilling and coring as both extraction and archaeology, and they move with deliberate restraint. They log depth, temperature, and regolith texture at each increment, because context is as valuable as the sample. A core becomes a timeline, and timeline integrity depends on contamination, discipline, and careful handling. In visuals, the core emerges in segments, wrapped and labeled like evidence in a forensic lab. The scientific payoff is larger than the moon, and the narration leans into that scale without leaving the ground. Earth's early volatile history was erased by plate tectonics and oceans, which recycle and blur ancient chemical signals. The moon kept a colder, quieter record of the same inner solar system mixing because it lacks weather and active geology. That contrast is why lunar samples still matter, even after decades of analysis. If lunar ice contains organics and nitrogen compounds, it becomes a chemical fossil with implications for habitability. It can constrain when volatiles arrived and how long they survived bombardment and thermal events. It can also test models of how habitable ingredients move between worlds, including whether delivery was continuous or episodic. The question hangs quietly. Are we reading a single catastrophe or a long accumulation of small gifts? ISRU therefore becomes a scientific revolution, not just a cost-saving trick, and that dual identity is the chapter's pulse. The same plant that makes oxygen also forces precise accounting of impurities, because machines demand clean inputs. Those impurities are the clues, and industry becomes the instrument that measures them with relentless consistency. Every filter change and every chromatogram becomes part of a larger argument about origins. Efficiency becomes the next tension point, because power is finite and time is expensive on a surface that punishes waste. Heating regolith costs energy, and energy comes from solar ridges or fission units that must be protected and maintained. A plant that wastes watts steals them from habitats, rovers, and instruments, and the trade is never abstract. Engineers, therefore, speak in yield per kilowatt and kilograms per hour, because those numbers decide architecture. A low-yield plant is a science demo, valuable but fragile, and it cannot carry the weight of routine operations. A high-yield plant becomes a logistics backbone that can justify new missions, new routes, and new safety margins. The difference is not just throughput, it is confidence, because confidence is what turns a plan into a schedule. At scale, even spare parts become a strategy rather than a scramble. Operations reveal a deeper truth about living off-world, and it is not glamorous. Chemistry is maintenance, and maintenance is culture, because systems only stay safe when people act predictably. Filters clog, valves stick, sensors drift, and dust finds every seal, especially the ones you trusted. The moon does not sabotage you, it simply refuses to care, and that indifference is the real antagonist. Artemis II's psychological unlock returns here as a requirement, not a memory of first steps. Crews must trust procedures, trends, and alarms under delay and fatigue, and they must do it repeatedly. Routine is what keeps a chemical plant from becoming a crisis generator, especially when a small leak can become a large loss. The calm voice in the headset is backed by checklists written in hard-earned caution. Radiation standards also reappear because production increases surface time, and surface time accumulates dose. More hours outside mean more exposure, and dose budgets must include industrial work, not just exploration. The common risk language now spans Orion transit, habitat sheltering, EVA, and plant maintenance, and every category competes for the same human hours. Safety becomes a scheduling problem as much as an engineering problem. The two-lander strategy becomes part of ISRU credibility, because cadence protects learning, and learning protects scale-up. If one lander stands down, the other preserves spare parts flow and keeps the chain from freezing in place. Without cadence, a broken pump becomes a year-long pause, and a year-long pause kills scale-up by erasing momentum. Artemis treats continuity as a technical parameter because it behaves like one. As propellant production grows, the narrative stakes widen beyond the South Pole, even while the camera stays near the shadows. A refueling node changes where missions stage and how they abort, because fuel is what makes options real. It also changes what science can be attempted, because mobility and return options expand together. When you can travel farther and still come home, you can ask bolder questions without gambling lives. Yet the chapter refuses a clean victory, because the moon resists simple industrialization and punishes overconfidence. Hydrogen still leaks, dust still abrades, and cold traps still threaten to be altered by our presence, even when intentions are careful. The doorway demands payment in discipline, and the payment is ongoing, not a one-time fee. The plant's numbers can rise while its ethical burden rises with them. The climax lands on a single idea, stated as a logistics equation and a cosmological claim, and it holds both at once. If Artemis can turn ice into breath and fuel, it can stay long enough to read deep time properly. If it cannot, the moon remains an archive behind glass, visible but unreachable in practice. The difference is not romance, it is residence. This is also where the transportation spine reasserts itself as the hidden dependency, because no surface system exists in isolation. None of this works without SLS and Orion delivering crews reliably to lunar space, again and again. None of it works without landing architectures that connect NRHO to the surface repeatedly, with predictable mass and predictable cadence. The plant can only scale if the bridge keeps delivering people, tools, and patience. ISRU is not a replacement for transport. It is what makes transport matter less per mission and less fragile per year. The more the moon supplies, the less Earth must throw uphill, and the less each launch must carry as life or death cargo. The bridge becomes cheaper to cross, and therefore easier to keep open even when budgets tighten. That is how infrastructure is born, by reducing the penalty for continuing. The transition to the final chapter is deliberate and unresolved, because the story is still negotiating with reality. Artemis has learned to live, move, and begin producing, and those are not small achievements on a hostile surface. The last question is what kind of permanent bridge this becomes, and what it changes about humanity's future among the stars. The moon waits in shadow, offering ice that can be burned, breathed, and believed. In early 2026, NASA standardized on SLS Block 1, protecting schedule stability over constant redesign, a lesson learned from decades when upgrades quietly stretched timelines. At 98 meters tall, it rises like a lit tower at dawn, then lifts with 8.8 million pounds of thrust from 4 LH2 LOX RS-25s, plus 2 5-segment boosters. Those engines, reborn from shuttle heritage, sip super-cold propellants, while the boosters add raw, grain-burning impulse that cannot be throttled, only trusted. The ICPS upper stage pushes about 27 metric tons toward TLI, enabling single-launch simplicity for crewed deep space departures and fewer assembly steps in orbit. Orion carries the crew's deep space lifeboat and habitat, a crew module plus European service module for 4 astronauts, 21 days undocked, with power, propulsion, and life support riding behind like a quiet spine. Autodock becomes the hidden gate, because docking reliability turns sorties into routine operations, and routine operations are what make a program feel permanent. With transport stabilized, the bottleneck becomes landing cadence and redundancy. HLS stays competitive because one lander cannot serve every mission forever, not when weather, maintenance, and mission goals pull in different directions. Starship HLS stands about 52 meters, needs tanker launches and depot refueling, and can deliver near 100 tons, changing surface scale from flags and footprints to cranes, shelters, and long-lived infrastructure. Blue Moon Mark II is about 16 meters, BE-7 hydrogen, 20-plus tons, aligned with ice mining and ISRU, where lunar water becomes oxygen and fuel, and logistics tighten around local supply. Methane scale and depot logistics meet hydrogen efficiency and staging, two philosophies aimed at one horizon. Sustained presence turns distance into data, and the moon into Earth's mirror and memory. Across this journey, the moon stopped being a destination and became an instrument, an airless archive that Earth cannot keep. Artemis II proved the machine can survive deep space without a heartbeat inside, while Artemis II must prove the harder thing. Humans can sleep, reason, improvise, and still trust the numbers. From there, the story turns on repeatability. Docking that works every time, landings mastered through deliberate de-risking, radiation turned from an unknown into a shared operational language, and polar sorties evolving into mobility, power, habitats, and maintenance that can endure seasons. At the South Pole, the permanent shadows hold ice like a library, but reading it demands restraint, zoning, contamination, discipline, and an ethics strong enough to survive schedule pressure. Redundancy becomes more than engineering philosophy, because 2 landers, 2 logistics paths, and verified margins are what keep cadence alive when reality breaks something important. And ISRU is the inversion point, where water becomes breath and fuel, and the moon begins to supply the bridge that keeps reopening its own doorway. In the background, SLS and Orion remain the spine, stable enough to carry routine forward, while the hidden gate, auto-docking reliability, quietly decides whether this becomes transportation or theater. If all of it holds together, Artemis Base Camp is not a collection of missions. It is a clock that keeps running, long enough for cosmology to become fieldwork. So, are we building a home, or opening a doorway that tells us where Earth came from and whether we can outlast it? Artemis suggests the answer is both, because a home on the moon is the doorway, and living there is the method that lets the archive speak. The proof will not arrive as a single flag moment, but as a chain of ordinary successes. Safe sleep after an alarm, a clean dock under glare, a descent repeated, ice sampled without rewriting it, and dose budgets met often enough to feel like policy instead of luck. When those routines harden into cadence, the moon becomes a cosmological laboratory in the most human way, by forcing us to practice permanence while we study beginnings. The moon has been holding the solar system's first light in its dust and its ice, not as a souvenir, but as a test of patience. If Artemis becomes a permanent bridge between Earth and deep time, then every habitat